Okay, today is May 12, 2025, and this is Physics 7. Here's the schedule. Today is Monday, 12 of May, 2025, and we are going to continue on the topic of refraction. Let's see what's coming, right? So the 1 week and a half from now is going to be exam 3. Okay. And let's see, exam 20, okay. 22, let's see, we finished 26. Let's say we finish 26 today, right? And I will add 26 to the exam. So far, we didn't do lab 6 yet, right? Let me erase that here. Change. Lab 6 is going to be right in here on Wednesday. Let's see, we're going to at least lab 5, right? Yeah, let's stay with lab 5. 9:40 to 11. The exam is 9:40 to 11:40. Okay, and then we are going to have a holiday, Memorial Day. Let's go to our notes. Okay, we're talking about different types of lenses. Planar convex. Planar convex is this lens here that I showed to you. This one, planar convex. And then we have other types of lenses, biconvex. Convex here and convex here, right? Both sides. Let's see if I have a. Yeah, I don't have an illustration of biconvex, unfortunately. Yeah, okay. And planar concave. Oh, you also have planar concave. It's going to be a negative lens. Okay, planar, but now the concave is going to be like that. All right, planar concave, biconvex, biconcave, concave, convex lenses can be either positive or negative, depending on the relative curvature. On the relative curvature between the two surfaces, okay? Can be either positive or negative, depending on the relative curvature between the two surfaces. And May 12, 2025, week number 14. And meeting number 22. The 22. Okay, so let me get something else here. Okay. Okay. Lenses refract light. Okay. Light goes through the lens, is refracted, And depending how the lens is built, it will either concentrate the light rays or diverge the light rays. Okay, lenses that concentrate the light rays are positive lenses, and lenses that diverge the light rays are negative lenses. Okay, and like I explained before, right? Just like in the case of the mirror, light rays that are parallel to the principal axis of the lens, and we're talking about collimated light rays. Collimated light rays are light rays that are parallel to the principal axis of the lens, are refracted towards the focal point. Light rays that pass through the second focal point are refracted parallel to the principal axis. Light rays that are incident at the center of the lens are not refracted at all. They pass through without any change in direction, because the lens is thin. It's assumed to be very thin. Assumed to be very thin. Okay? If you were a thick lens, would be different. And let's and I believe I showed that to you before, right? So let me show it again. Here you go. Planar convex lens. We start with the lens. We draw the principal axis of the lens. And we have this collimated light ray that's going to pass through the lens. Here you go. Approaching the lens. Is the incident with the planar surface. And then now it's going to refract, because the angle of incidence of this light ray is 0 degrees. The light ray will move forward without any change in direction. Okay, but now that it is incident on the other side of the lens, which has a curvature. Okay, here is the plane tangent to the curvature of the lens. This light ray is going to be refracted into the other medium. So here you go. Here is the normal with respect to the curvature of the surface. Okay, here is the through-by light ray. We do that just for the sake of reference. Okay. And then this light ray, because it's going from a medium of high refractive index to a medium of lower refractive index, is going to bend towards the principal axis, right? Or going to refract away from the normal direction. That's my first light ray. Now we can have a focal point there. Okay, here you go. Another collimated light ray is going to be concentrated towards the focal point. Okay. And let's go through the process of forming a real image by positive lens. So instead of keep on drawing lenses with curvature, we just represent the lens by this arrow with this double arrow illustration. Okay, that's representation of a positive lens. A negative lens is all the way around. Okay, positive lens, and I can draw a negative lens as well. Negative lens is going to be drawn like that. Even better, I'm going to make it simpler here for all of us. And for me, right? Huh. Interesting. Didn't work. Let's try another one. Oh, one is upside down triangle. Doesn't look like it has an upside down. Oh, here you go. Yeah, we have an upside down triangle. Here you go. But now I no fill. The line is going to be black. I'm going to make it thicker. Okay, this one. More students coming. And I am going to hide the thing. White. Yeah, here you go. Gonna make it thicker. I'll make this one thicker as well. Okay. Group. Yep. Let's see if I can invert. Yeah, I can invert. Good. That's the representation of a negative lens. Representation of a positive lens. A positive lens. Representation of a negative lens. Okay, so go back here. Now we started building our system. Here you go. One lens, its corresponding principal axis, right? Focal point behind the lens, focal point in front of the lens, F and F prime. Object, light ray parallel to the axis, to the main axis of the lens. And this light ray is converged towards the focal point. Light ray that passes through the focal point of the lens. Okay, the light ray that passes through the focal point of the lens is converged towards the focal point, but they end up being parallel to the axis, the principal axis of the lens. Right, and then right at this very moment, I already know where the image is formed, right? I already know that the image is formed right here where those two light rays converge. Okay? But I can also draw a third light ray just as a backup. Third light ray passes through the center of the lens, and because the lens is very thin, we can approximately state that it's not the light ray doesn't change its direction. Okay, so just goes through the lens in the same direction it started. Okay, so here you go. That's the distance of the object. That's the distance of the image. Okay. The object has a size, the image has another size, I. Here's the focal distance, right? And just like before, we're going to have the same equation that we have for the spherical mirrors. And let's get it. Let's hunt for these equations. Just by doing the similar triangles, that's the argument that we use to find those equations. Here you go. Let's see if we can get everything at once. Yeah, looks like I'll have to. We have this equation here. H naught over Hi, and you still have the magnification. The magnification M is equal to M Hi over Ho. And that's going to be the magnitude. Right in here. And we got the same for, which is also equal, right? To Di over D naught. Okay. That's the equation that, and let me come up with a table. Here you go. Comparing a lens with the mirror, comparing lens with mirrors. Concave mirror concentrate a collimated light ray. But a concave lens diverge a collimated light ray. See, I put in the same color, red here and red here. Okay. Convex lens diverge, convex mirror diverge a collimated light ray. Whereas a convex lens diverges, concentrates, mirror, diverge, concentrates, collimated light ray. Focal point in front of the mirror, behind the lens, with respect to the object, don't forget. Okay, everything on the same side of the object. Here you go. Let's put on the same size as on the same side on the same side of the object. On the other side of the object, on the other side of the object, on the other side of the object. Second focal point, yes, we have for the lens, but not for the mirror. Okay, so what we are having here you go. If the mirror, if the object is past the front focal point, the image is formed past this focal point here, on the other side of the focal, on the other side of the lens. Okay. And just like the mirror, if an object is far away from a second focal point, past the second focal point F prime, the image formed will be behind the lens, to be real and inverted. If an object sits at the focal point, the image formed will be improper. Just like the mirror, right? If an object sits at the focal point of the mirror, the image form is going to be improper. There will be no image form because the light rays do not intersect each other. And we can even draw it. Let's see if I have it here. Improper. Oh yeah, here you go. Improper image formed by a positive spherical lens. Here you go. So we have. Let's do it step by step, right? We start. We start with the lens. Everything else but the lens. Only the lens. Here you go. And then we keep on adding. Oh, we keep on adding the elements that we need. Here you go. Principal axis. What else? Focal point behind the lens. Focal point in front of the lens. And then I'm going to draw the object. The object, in this case, the object is going to be at the focal point. All right. And then we can start working with the light rays. Light rays. Let's see. Yeah. Next one is going to be light rays parallel to the main axis. Converge towards the focal point. And by the way, note that I okay, let's do it in the next one. Okay, yeah. Don't need that. Converge. I don't want it here. I want it in the other one, in this one here. Oh. Okay, now at this point, note that this distance here is equal to this distance, right? Because we form a parallelogram. Form a parallelogram right here. You got the length of this side is equal to the length of this side. Next, and then we have a light ray that passes through the center of the lens. What am I missing? I'm missing here the origin of my axis, right? Here you go. Let's put it here. 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 And here as well. Okay. Next, gotta put it here. Here you go. Because this distance is the same as this distance, those two light rays must be parallel to each other. Be parallel to each other, forming a parallelogram. The third light ray is the one that passes through the front focal point, right? And it will never intercept the other two light rays. It's not going to be parallel to each other, but it still wouldn't intercept the other two light rays. That's the improper image. Can erase this one. The image is improper. Now let's talk about virtual images formed by a positive spherical lens. And then we're going to do exactly what we did before. Start from scratch. Start with the lens, and then we put everything else afterwards. The main axis. Yep. I'm going to label this main axis 0, X. Make it nicer too, black and thicker. Okay. Origin. The focal points, F and F prime. Object between the front focal point and the lens. And we go ahead and we go light rays parallel to the axis. Okay. What is going to happen? This light ray is going to converge towards the focal point. Okay. We can also come up with another light ray that passes through the frontal focal point. You go. Okay, passes through the front focal point, through the tip of the object, right? And it doesn't matter. It's not intersecting the lens. Okay, it is as though as the lens is infinitely long and can afford to affect the path of the light ray. Go. And what I'm going to do, I'm going to put this extended line here, this line that extends my lens. Okay. And then this light ray will have to be parallel to the axis of the lens. And then we can come up with this third light ray as well. The third light ray is the one that passes through the center of the lens. Note that all those three light rays, they are diverging from each other. Okay, if they're diverging to the right side, they must be converging on the left side, right? So in this specific case, the image is going to be forming the same side as the object. So let's go ahead and extend each one of those light rays. That's the key to form the image. Extend this red light ray. We're going to extend this blue light ray, notice that I'm dashing the line, right? Dash the line. This one right in here. It does intersects the first light ray and the third light ray. If we did everything right, is going to intersect the other two in the same point. And let's make it dashed. Yeah, okay. And finally, we have the image formed right behind the object. Yeah. Turn to back. Okay, this type of image is going to be upright virtual. Okay, so get used to this technique, okay? And then we can start talking about the spherical lenses. Okay, here you go. Here's the illustration of my spherical lens. Main axis, focal point. Now the regular focal point is going to be on the left side, right? The image of the focal point is F prime. Let's see. Compare that, right, with the positive lens. We can put the object, let's say, between the focal point and the lens and start drawing our light rays. Collimated light ray should diverge the light. The lens should diverge the light. Okay, and the light ray that passes through the center of the lens is going to pass with no change in direction. And the light ray that goes through the focal point on the other side is going to diverge parallel to the axis. Okay, here we go. The first light ray, its extension must pass through the front focal point. Here you go. The second light ray is intersecting the second one. And even the third light ray also is intersecting the other ones right in here. And we form this virtual image, the smaller virtual image. Okay, I'm putting here the origin of the axis. Okay, so for positive lenses, let's write it down. For positive lenses, if an object is far away from the second focal point F prime, the image formed behind the lens and it to be real and inverted. Okay, if an object sits at a second focal point, I already said that, right? Let's see here. Yeah, even if I have said that, let's repeat, right? Oh, no, already, okay. For a positive lens, there you go. For a positive lens, a positive length if an object. Okay, so erase that. What else you have to know? You know, converging lenses, positive lenses, right? Focal point is greater than 0. Diverging lenses, focal point is focal distance, not focal point, focal distance is less than 0. And then you can, you know, to learn more about that, you can even, you know, go to our simulation of lenses. Simulation of lenses, geometric optics. Let's see if this one, I don't like this one. I like maybe this one here. Let's see. Yeah, here you go. Right, as I can go ahead and move my object to see what happens to its image, right? If notice 1, 2, 3, 4, if I put the object at a position that's exactly twice the focal distance, the object that's formed behind the lens is going to be inverted, but the distance is going to be the same, just like in the case of the mirror, right? Further away, we can move it further away. The image gets closer and closer to the focal point as the object moves further and further away. As it gets closer and closer, the image is formed further and further away from the focal point. See that? And at this point here, just like you saw, right? We form an improper at the focal point. The object at the focal point, the image formed is improper. And as we move the object past the image of the focal point, the image formed is going to be virtual, large and larger than virtual. Okay, so let's copy this. Play with the simulation. And now, let's see if I can. Let's see if I can invert this lens. There must be a way to invert this. Okay, that's a positive lens. And let me see the convex lens. What a shame. Okay, looks like I have to change. Oh yeah, okay, that's how you do it. You move the focal point, right? Focal point, lens, positive lens, focal point on the other side, negative lens. Okay, that's how we change. See the focal distance, negative now. Okay. Distance of the image is negative number. It means that's going to be sitting on the same side of the object. The height is positive. It means that the lens is upright. As I move away, the image gets smaller and smaller. As I get closer and closer, the image gets larger and larger. Okay? It all comes from that equation that I spelled out before. Okay. So let me just copy and paste here what we just said. Okay, so here we go. for a positive lens. Oops, not this one. Okay, so continue. No. Huh. Well, that's a shame. It is number 4 here. Okay, it's supposed to be number 2. Yeah, here you go. Number 2. And now this one is supposed to be number 3, right? Oh, let's put number 2. Yeah, sometimes this numbering doesn't work well in Word. I do not know why. And then let's fix this one too, right? All right, so here you go. Object placed in front of a lens at a position greater than 2f. Light ray comes from the tip. Object, parallel axis, refer to parallel axis, parallel to the light rays, parallel to the axis. Refract towards the focal point, passing through the image of the focal point, f prime, and the light is refracted parallel to the principal axis of the lens. Passing through the lens of the lens, follow a path, an unrefracted path. Follow an unrefracted path. Right? The intersection of these 3 light rays define the tip of the image. So the tip of the position, define the position of the tip of the image of the object. The result is a real object. Image is real, inverted, and smaller. We place the object at a position between f and 2f, so it's going to be like that, O, the O is less than 2f, greater than f. I see, here you go, DO. Here you go, we're going to do that. Greater O than 2f. And we can even come up with another one too. Here you go. Yeah, here you go. What about DO equal to 2f? Okay? Just like before, object real, image is real, inverted, and same size as the object, same size of the object. The object. Okay. Light ray coming from the tip, it's the same thing, right? That we had before. Object real, image is real, inverted, and larger. Unrefracted. Go, let's invert it here. Oh, this one here. Okay, so here you go. Move it. Just Okay, so here you go. Object, first one, placed in front of the lens at the position d naught greater than 2f, right? Parallel, light rays parallel, Object real, image is inverted and is smaller. What else can you say here? Smaller, position, we're gonna put one more here. Position of the image closer to the 2f. closer to F, right? As you move the object further and further away from the lens, the position, right? Take a look. The position of the image gets closer and closer to the focal point. When the position of this object is very large, the image is going to be formed exactly here at the focal point. Okay? Now, light rays. I think I have to put one. I think it's better if we put one here. Yeah. Coming from the tip of the object. Well, light ray. The object. Try to organize it here, parallel to the axis. And now we don't need to put that because it's going to be repetitive, right? And then this one here is going to be number 2. Just organizing it better. Okay, object is real. Object real, image is real, inverted. Same size of the object. Equal to F. Same size of the object. And formed at 2F. Right? Just take a look here. I'm gonna place it 1, 2, 3, 1, 2, 3. I'm gonna place it right in here. Okay. I want the focus to be exactly. No, this one here. Okay. 3. Here you go. Better. F equal to 3. D naught is 6. Di is 6. Okay. And the size is the same, but it's just inverted. Okay. So object real. Image is real. And I'm going to do like that. Here you go. Image is real. Image is real, inverted, same size of the object and formed at 2F. At a distance 2F behind the lens. And then we can, let's see, object placed in front of the length at position between, right? F and 2F, let's see. Yeah, that's right. We can do like that. Here you go. Let's do this way. Less than 2F, greater than F. Okay? And then we do not need the rest, right? Object real. Image is real, inverted and larger. Inverted, larger, comma. And formed, let's see where it's formed. Go. Larger. And formed at a distance greater than 2F. And formed at a distance greater than 2F. Like that. Object placed at F. a distance f in front of the lens at the focal point f prime. Okay. Object, real. Image is improper. Image is improper. What else I can say? Infinitely large, right? I can say that infinitely large. Large. Because the light rays don't intersect each other. At the eye, and now I'm going to, let me use this one here. At the eye, I'm going to copy and paste it here. Here you go. Arrow, arrow. This arrow here. This one here. And where's the infinite? Where's the infinite? Oh, right in here. Okay. We don't need that. Okay, object plate at distance f. And finally, five less than f in front of the lens. Okay, and let's take a look at our simulation. You go right in here, the improper image. And now what about here? Right? Here. We go A, object real. Image is virtual, upright, larger, and formed at wow. Let's see. Formed at the eye, right? Less than DO because it's negative. DI less than DO because it's negative. Right? But I can also state or magnitude of the I is greater than magnitude of the O. I can say that too. You go. Yeah, like that. And I don't need anything else more. That's all we have. Let's see, can I do better than that? I think I can do better than that. Instead of keep on repeating for real objects, right? Here you go. I'm going to for real objects. Okay. Object. Whenever we have an object that's not real but virtual, then the thing changes. Okay. Okay. Now we can do like that for real object. Object placed in front of the light coming from the Okay, we have to repeat that only once, right? 1, 2, 3, 1, 2, 3 light rays. And then image formed is. Okay, image is real. Okay, I don't need that. See here. I'm gonna put like that. Image form is. Go. Now, real. Right? Image formed. And I can image form this. I don't need that. Here you go. I replace for object real, right? Replace with image formed. Image formed this. One more student. Let's see. What time is that? 10:38, almost our time. So image form is okay. And here you go. It's positive, right? Because we are dealing with the magnitude of DI. DI, the regular DI that's negative is more negative than DO, right? That's why it's less. But if we take the magnitude of that negative number, the magnitude of DI is going to be greater than DO in number 5. Okay. That's for a positive Fourier convergent lens. F greater than 0. Let's see here. Like that for real objects. Yeah, here you go. Divergent lens. Now we do the same here for divergent lens. For real objects. We don't have to repeat all that stuff, right? Parallel light ray, blah, blah, blah. Image for real objects. For real object. Object placed in front of the lens. And then we can see from our go. It's always going to be smaller, right? See that? Always. And it's going to be between the object and the lens. Object placed in front of the lens will always, object placed in front of the lens. Image formed will always be virtual, upright, smaller, and formed between 0 and D naught. So it evolves in a logical path, okay? That's the simplest one. Let's take a look what we saw so far. Here you go. Let's take a look at here you go, this one that I want. This one that I want right in here. What we have covered so far. Index of refraction is Snell's law, total internal reflection. We're skipping polarization, spherical lenses. Formation of image by lenses, okay? I'm going to skip this one. Oh, wait a minute. Scene length equation is that one that we introduced? Right, lenses. Let me just double check here. While plus. Login. Come on. Login. Good. Physics 7. While course resources. And launch. Got 26, right? Refraction. Scene length equation. Yeah, and then that's what I cover, right? Scene length equation. That's the equation for the scene length. If the lens is not seen, this equation changes slightly. Okay, so we did cover scene length equation. And we are not going to do lens in combination. Scene length equation we did. Skip. Okay. And we're going to do the human eye after the break, okay? So let me take attendance right now. Right here. Lecture 12. Abir, Ahmad, are you there? Yeah, I didn't hear you, Abir. Let's see. Okay, so I see Abir. I'm going to give attendance to her. Can you hear me, Abir? Okay, let me put a star here under her name. Next, Nestor, right? Nestor Alvarado.
Yeah, I'm here.
Thank you, Nestor. Monte Ambarchian. Someone is opening the door, right? Let's see. Mute. Okay. Can you hear me? Okay, so I hope you can hear me. So if you cannot hear me, let me know. Monte, I don't see Monte here.
I'm here.
Monte?
Yes.
Okay, good. Thank you. Next, Isabella. Isabella Ballesteros. I don't see Isabella. Next is Justus. Justus.
Okay, so
Here, Professor.
Thank you. Next is Alexandra Romanov, right? Now is Alexandra Romanov.
I'm here, Professor.
Okay, let me change your name here. Romanov. Benjamin Carvajal. Gotta change also the position here in the insert that. Okay. This is what. Okay. Benjamin, are you there? Okay, thank you, Benjamin.
Sorry, Professor, I'm here, but my mic isn't really working well.
Okay. I'll be right. Thank you.
Yes.
Next is Elizabeth Castellano. Man, this. Okay. Thank you, Elizabeth. Next is Natalia Cordoba. I don't see Natalia. Jacqueline Delgadillo.
Here.
Thank you. Jenny Diaz. Let me see. Okay, I don't see Jenny here in my list. Valerie Diaz.
Here.
Thank you, Valerie. Juan Escalera. I see. Thank you, Juan. Bianca Eloki. Thank you. Next is Edwin Gonzalez. Jenny is just joining us now. Thank you, Edwin. Eli Gonzalez.
Here.
Thank you. Let's see. Huh. Let's keep on going. Manuel Hernandez. I don't see Manuel Hernandez here. Next is Samantha Hubert. I don't see Samantha either. Jenny is taking a long time to join. Let's see. Nope, she wasn't able. CJ. CJ is not here. Amber Lopez. Doesn't look like Amber is here. Next. Arely Lopez. I see Arely here. I don't hear from her. Let's go to the next one. Genesis.
I'm here.
Thank you, Genesis. Next is Mary. Thank you, Mary. Talia. I don't see Galia here. Oh yeah, I see Galia. Can you hear me? I'm gonna put a star here under her name. Next is Ramon Olivares.
Here.
Thank you, Ramon. Taylor Horn. Taylor Horn. I don't see him. Next is Jeremy Pittman. Jeremy Pittman. I don't see Jeremy. Next is Stephanie Ramos. Thank you, Stephanie. Next is Leslie Rios.
I'm here.
Thank you. Alexandra Roman already called her. Jason Street.
I'm here, sir.
Thank you. And last here, not least, Hema Torres.
I'm here.
Okay, thank you. So let's take our break now. 22. We have 1, 2. Yeah, good. Break. 10:51 a.m. to 11:06 a.m. Okay. I see you in 15 minutes. I am back here. Here is Here is our notes, right? And what I want to do now, what I'm going to do the human eye, and everything else we're going to skip. Human eye is important for you, right, folks, since you are in this field. And the human eye. The human eye is an optical device, okay? It is an optical device. It behaves just like a positive lens, a convergent slash positive lens. And a very simple model of the human eye is that the lens would be the one that provide most of the optical how do I say? Most of most of the optical characteristics of the lens, but in real life, it's not just the lens that bends the light that comes from outside. The cornea also plays a role, okay? A role. Behave just like a convergent positive lens. To first approximation, let's put it here like that. To first approximation, we can say that the lens of the eye is the one that provide all the refraction to the light. However, in reality, it provides most of the refraction. Most of the refraction, okay? With some of it, most of the refraction, with some of it done by the cornea. By the cornea. Okay, let's take a look. I once saw an article that described that very nicely. Unfortunately, I didn't. Human eye. Human eye. Here you go. That's how the human eye looks like, right? We have, that's the lens. And the cornea is this bluish layer in front of the eye. Okay. And we also have the vitreous body that also provides some of the refraction as well of the image, but most of it comes from the lens. Okay. So cornea, the vitreous body, and the lens. And let's take a look at the Wikipedia. Let's see what they say about the refractive power of the light of the eye. Refraction, right? Let's take a look here. Refraction. Okay, refraction in the cornea. Okay. So the cornea definitely The effective aperture to differ slightly from the physical pupil diameter. The entrance pupil is typically 4 millimeter. Let's see if we have some. Yeah, it looks like they talk only about the refraction of the cornea. Okay, let's see the lens. Yeah, unfortunately, he doesn't compare the amount of refraction by each of the elements of the human eye. Okay, but some time ago I saw it somewhere. I don't remember where. The lens, the effect in the refraction is mostly due to the lens, and unfortunately, this Wikipedia article doesn't discuss that. Okay, but let's leave it this way. Okay, the human eye is an optical device. It behaves just like a convergent positive lens. The first approximation, you can say that the lens of the eye, is the one that provides all of the refraction to the light. However, in reality, it provides most of the refraction, with some of it done by the cornea and the vitreous let's see, the vitreous. Yeah, let's go back in vitreous body, right? Vitreous body. But there are some other interesting things about the eye, okay? Whereas regular lenses that we artificial lenses, okay? Whereas let's see, whereas artificial lenses that are manufactured are rigid, okay, comma. The human lens is a flexible one that can change its focal length, okay? Its focal length. Our lens is bent by the muscles of the eye. Into different radii of curvature. As we age, okay, the lens becomes harder and does not bend as much, does not flex as much. Does not flex as much, okay? And we lose our ability to focus on objects that are closer to the eye. Okay? So regular lens, so in short, right? In short, regular lenses are rigid. However, the lens in the human eye is flexible. And then we have two adverse effects. And oh yeah, here you go. here's the normal eye, right? Normal human eye. And here, that's how I am describing the human lens, a convergent lens. For a normal eye that's very round, the image forms exactly there at the retina. Okay? But if you're someone just like me, okay, I have a very nearsighted eye. The eye becomes very elongated. Has nothing to do with the lens, it has to do with the shape of the eye. And opticians can see that when they examine you, okay? The lens can, depending on the shape of the eye, it comes to a point that the lens can no longer focus the light at the retina, even though it can vary its focal length, okay? So if you are very nearsighted like I am, the image is not going to form in the retina right here, but it's going to form before the retina. And in order to correct something like that, you need a divergent lens. Okay, why is that? Because if you use a divergent lens, light that comes from the outside is going to diverge just a little bit to the point of increasing the focal distance of the lens, okay? That's what the divergent lens does. It helps the lens of the eye to focus its light, corrected with a negative lens, Now we also have the other thing, a far-sighted eye. Instead of elongated in the horizontal direction, it's going to become elongated in the vertical direction. And the image is formed past the retina that stays right in here. In order to correct for this problem, we have to use a converging lens that's going to shorten the focal distance of the lens of the eye. And the object will be focused at the point right there at the retina. Okay, that's what you have to know. So let's write it down. Two adverse conditions of the human eye. We're not going to talk about astigmatism here, okay? Just the nearsighted eye and the far-sighted eye. Here you go, nearsighted eye. In a nearsighted eye, the image of the object is formed before the retina. This is because the eyeball becomes stretched or longer, and consequently, the image can only be formed before the retina. For the far-sighted eye, the image of the object is formed after the retina. That's because of the eyeball becomes shorter, and consequently, the image can only be formed after or behind the retina. Okay. To correct for these conditions, okay? To correct for these conditions, a nearsighted eye must wear a negative lens, which effectively increases the focal length, which in combination with the eye lens, which in combination with the eyes lens effectively increases the focal length of the whole set, right? Negative, and by set I mean the negative lens and the eyes lens. A far-sighted eye must wear a positive lens. Okay, in both cases, far-sighted lens where a positive lens, which, okay, let's write that down here. I'm just gonna copy this model, this template, right? A far-sighted eye must wear a positive lens, which in combination with the eye's lens effectively shortens the focal length of the whole set. The positive lens and the whole set, I mean, the positive lens and the eye's lens. The positive and eye lenses. Like that. Better, right? We call the positive, the negative, and the eye's lenses. Better, right? So one negative lens combined with a positive lens effectively, right? Increases the focal length of the set. Similarly, one positive lens, one negative lens, which diverge, right? Remember, which diverges light combined with a positive lens effectively increases the focal length of the set. One positive lens which converges light, combined with another positive lens effectively decreases, right? Decreases the focal length of the set. Can you picture that? Okay. If the lens that's in front of your eye is converging the light, it means that when it acts together with the lens of your eye, the focal length of the set is going to shorten. It's going to shorten. It's going to increase, right? For a negative, it's going to increase. But if the lens is positive, it's going to decrease, okay? Negative lens increase, focal length. Okay. We can live this way. Okay. Okay, and what else we have to know? In addition to the curvature of the lens, which is affected by the ciliary muscles, the pupil of the eyes can also be changed in diameter to let more or less light pass, right? The pupil of the eye is that black dot that everybody sees. Is the window to the retina. That's what the pupil is the window to the retina. That's where the light passes through. But its diameter can change it between 2 millimeters and 7 millimeters, depending on the amount of light. Okay? If you have more very strong light incident in your eye, the pupil is going to close. In a very dark environment, the pupil is going to dilate. Okay? In a very dark environment, I'm concerned about the 7 millimeters. I believe it's 9. Let's take a look. Largest diameter of the pupil. I see you can go all the way up to the pupil's eye. You go all the way up. It says up to 8 millimeters. Okay, my artificial intelligence. I have seen 9 millimeters in other books. Okay, but he's saying it's 8 millimeters here. Or to 8 millimeters. Let's see other references here. function, effect of light. Oh yeah, see, 9 millimeters. Okay, so let's see. The pupil gets wider in the dark and narrower in light. When narrow, the diameter can be between 1.5 and 4 millimeters. In the dark, will be the same at first, but will approach the maximum distance for a wide pupil, 3 to 8 millimeters. However, in any human age group, there is a considerable variation in maximum pupil size. For example, at the peak age of 15, okay, depending on the age too, right? The darker that pupil can vary from 4 to 9 millimeters with different individuals, okay? So you can say anywhere between 1.5 to 9 millimeters. 1.5 to 9 millimeters. Okay, in a very bright environment. So it is as though as the eye has some sort of photodetector there, organic photodetector, right? That can measure the light intensity and controls the pupil size from there. So it is as though everything is integrated, right? Nowadays we can do that with regular optical devices. Okay, and we have a diaphragm that works just like a pupil. We have the lenses of a camera, for instance, right? That work just like the eye's lens. And if you combine one lens with the other one, if you use two lenses, right? Two lenses, two artificial lenses, and change their relative distance, you can also control the focal distance of the whole set. Okay? There's no need to deform the lenses like the lens in the eye is deformed. In a very bright environment, the pupil shrinks in size. In a very dark environment, it increases in diameter. Okay? Increases. Pupils shrink in size in a very dark environment. The curvature of the lens. That's what you have to know. Okay, for this book. Let's take a look for this material. Let's take a look at the book here. Lenses combination. We are not going to do that. Okay, we don't have time to do that. But here you go. The aqueous humor too. Okay, affects. Yeah, I should have put affects the refraction. Cornea, the aqueous humor, and the vitreous humor. Let me fix that there in my notes. Most of the refraction, some of it done by the cornea. The vitreous, the aqueous humor. And the vitreous body. Aqueous humor. Aqueous humor. Okay. Retina right here, we have the optical nerve that sends the information to the brain. And don't forget that this lens projects an upside down image here in the cornea, right? But then how come we don't see upside down, right? We don't see upside down because the brain is just this computer, very advanced computer that invert the image for you. Okay. Here you go. That's how a distant object is formed. The image of a distant object is formed upside down. Okay. Look at the curvature of the lens. it has a very large curvature radius, right? But for a closer object, the curvature must become smaller to refract more the light. And then he says, tense the lens. Okay, and here how we do to fix this problem with nearsighted individuals, right? Why is nearsighted? Because the closer the object is, the easier the image is formed. Okay, that's why we are called. That's why we are called. I mean me, myself, one of those, right? That's why we are called nearsighted. Because to see better with no correction whatsoever, the object must be very close to you. And here's the lens, the diverging lens, that effectively increases the focal distance of the eyes lens and the corrective lens. Okay, and all the way around for the farsighted individuals. Farsighted is something that we become farsighted at older age. Okay. Okay, so that's what we have here for this chapter. And let's take our break a little bit early, and so we can start chapter 28, okay? It's 11:34 right now. Let's see if there's anything else. Angular compound aberration. Yeah, we're gonna skip the rest. Just stick right with those. Okay. So break 11:35 a.m. to 11:50 a.m. Okay, so I see you in 15 minutes. Yeah, okay. Okay, thank you. Stop. I am back here. Let's see. Stop sharing. Let's see if I'm doing something right. Here. There's 1, 2, 3. Okay. Someone is trying to come in, right? Here you go. And now what we are going to do, we're going to skip we'll skip chapter 27 and move to chapter 28. That's going to be the physics of the 20th century. Right in here, that's going to be a special relativity. And yeah. Okay. And let's see. Yeah. Oh, here you go. It's one of those crazy series that nobody believes. at the beginning. It was so far out. Special relativity was just so far out of the imagination of scientists that they couldn't believe it was true or not. Okay, this is the physics of the 20th century. Up to now, we're dealing just with the physics up to the physics of the 19th century. Okay, special relativity, the theory of special relativity was formulated by Albert Einstein in the first years of the 20th century. What Einstein got was something that was both very simple, very simple to formulate, and yet very counterintuitive as well. Also, it led to results that were difficult to believe, that were very difficult to believe. See. Now it's stuck here. Let's see if I can get rid of this thing. Okay. What Einstein got was something that was both very simple to formulate and yet very counterintuitive as well. Also, it led to results that were very difficult to believe. It was so counterintuitive that it took a long time for the scientific community to accept it as a fact. Okay? If Einstein won his Nobel Prize, and he should have won not one, but two, or maybe even three Nobel Prizes, okay? Nobel Prize. It was not for special relativity, but for other contributions. And if you go to the Nobel Prize website, other contributions, namely, the Brownian motion and the photoelectric effect. The Nobel Prize committee didn't mention special theory of relativity or the general theory of relativity, okay? That's so. Imagine if Einstein had came up just with the special theory of relativity and wouldn't have made any contributions on the Brownian motion or the photoelectric effect. Most likely he wouldn't have won the Nobel Prize. And in a way, he deserved not one, but three, okay? The Nobel Prize that he won for his contribution to Brownian motion and photoelectric effect, another Nobel Prize for the special relativity, and another Nobel Prize for the theory of general relativity. He deserved three, not one. The Nobel Prize, let's put it this way, the Nobel Prize this Einstein won was for his contributions to Brownian motion and the photoelectric effect. No mention was made for his theory of the special relativity or the general theory of relativity. We're not going to study the general theory of relativity, okay? But let's go there to the Nobel Prize. Let's see here. Nobel Prize. Let's see, of physics. Einstein Nobel Prize of physics. Let's see here. They have this specific mention physics. 1921 Nobel Prize in Physics for his service to theoretical physics, especially for his discovery of the law of the photoelectric effect. Okay, no mention of the theory of special relativity, no mention of the theory of general relativity. And it took almost 20 years for him to get this Nobel Prize. The work was around at the beginning of the century, 1904, 1905. And let's see, 1922, right? Let's take a look here. 1921, Nobel Prize of Physics. I want to get the actual Nobel Prize committee. Okay, right in here. Nobelprize.org. Do you see that? That is Stockholm, right? Okay. Born prize motivation for his services. Yeah, they didn't say anything about Brownian motion. They said only about the photoelectric effect. Okay. And what about special relativity? Here's the actual website of the Nobel Prize, right? Let's take a look here. Here's the main page, right? The home page. And then if we go back here, we have the page that they came up for Einstein, right? Let's see if they say anything about Brownian motion here. No Brownian motion whatsoever. Special theory of relativity. Let's say no. See? Relativity, no. But just the photoelectric effect. Just the photoelectric effect. Okay. And the interesting thing about that is that Einstein was a Jewish, right? And during the Second World War, he was being persecuted by the Nazi there in Germany. And the Nazi in Germany, they were rejecting every theory that would come up from any Jewish people. And they would say that all that theory of Einstein was just garbage, right? That's what the Nazi would say. And among one of those Nazi scientists was a guy that studied the photoelectric effect, okay? And it is as though as the Nobel Prize committee was trying to tell the Germans, right? You know what? We're going to give a Nobel Prize, even though you have a Nazi scientist that did lots of work on the photoelectric effect. We're going to give a Nobel Prize on the photoelectric effect for a Jewish. It looks like they were saying something like that to the Nazi, right? And the guy and the, let's see, the Nazi scientist, I'm trying to remember his name, Nobel Prize for the photoelectric effect. It's not just Einstein who got the Nobel Prize for the, let's see, photoelectric effect. Oh, I'm gonna remember the name of that guy. What's his name? Nazi scientist who won the Nobel Prize. No. Heisenberg, no, Nobel Prize in Physics. Heisenberg was a Nazi. No, it's not this guy. It's another one. Philip Leonard. That's him. Okay, Philip Leonard. He also studied the photoelectric effect and okay, and he won the Nobel Prize too, as far as I remember. Yeah. Let's see. This was shown, the photoelectric constancy was cited when Einstein was awarded. Leonard received the 1905 Nobel Prize in Physics, okay? For recognition of this work. So he won in 1905, Einstein won in 1921. And this guy would reject all the theories from Einstein just because he was a Jewish. 1905, let's see. I want to go to the Nobel Prize, 1905. Nobel Prize in Physics. Okay, summary. Here you go, Philip Leonard. Let's see what his contributions were. Nobel Prize for his work on cathode rays. Cathode rays, not the photoelectric effect. Okay, he worked with the photoelectric effect, but his Nobel Prize was on the cathode rays, not for the photoelectric effect. Okay. Okay, so let's go back here, right? Let's talk about, so Einstein, he came up with two laws for his special theory of relativity. And let's talk about the laws that we have seen so far, right? In Newtonian mechanics, we have three laws of motion. In reality, it's only two laws because the first law is just a consequence of the second one, right? Plus the law of gravitation. In thermodynamics, we have four laws, the zero law of thermodynamics, the first, second, and third laws. We just went through the four laws of electricity and magnetism, Gauss' law for electric and magnetic fields, Ampere's law, and Faraday's law. All those four laws, all these four laws are now known as the Maxwell's equations. Which was the guy that gave the final touches to all those four laws. We talked about the ray optics, the law of ray optics. Okay, the law of least time, the refractive index law, and there's another one, the light ray behavior. Light ray behavior, okay? And now we're going to see two more laws that was formulated by Einstein in his special theory of relativity. Later on, Einstein started with the theory of special relativity theory, right? Later on, he's extended. Notice that he said special, right? Special. Why is it special? It is special because it applies only to objects moving with constant velocity. Okay. Later, in this case of special theory of relativity, it is special because it applies only to referentials that move with constant velocity. Okay. Later on, Einstein formulated the theory of general relativity, which applies for accelerated referentials. It's more generic. In other words, it is more generic than the first one. Okay. And then, so here's the difference. I'm gonna repeat again the difference between special theory of relativity and general relativity: constant velocity versus variable velocity, or accelerated motion, accelerated frames of reference. So when Einstein proposed his theory of relativity, it's a fascinating history behind that. Okay, physics was in a crisis mode. They were starting to observe. They thought that they have at that time, at the end of the 19th century and beginning of the 20th century, physicists thought that they had figured out the universe, that there was nothing else to learn, nothing else to discover, nothing else to understand. They saw that they got it pinpoint. Okay, but then little by little, they start to see some experimental results that could not be explained by those so powerful theories that they had at the time. Okay, so the theories that they had at the time was those here, Newtonian, thermodynamics, and electricity and magnetism. Those are the theories that scientists thought that they got it. There was nothing else to learn. Okay, so we can write down like that. At the time of Einstein, just before the time of Einstein, just before Einstein, right? Physicists thought there was nothing else. There was nothing else to. There's nothing new to discover. Okay, they thought they had all the laws they needed to explain the universe. That's because Newtonian mechanics, the laws of thermodynamics, right? Geometrical optics too. You can put the geometrical optics here as well. Geometrical optics, and the other one was the laws of electricity and magnetism had been extremely successful. Okay? However, physicists start to find holes in their understanding of the universe. Okay? So one of the problems that they were having problems, one of the things that they were having problems, right? In thermodynamics, they could not explain theoretically explain the black body, the problem of the black body. Hopefully we'll have time to cover that, okay? The so-called catastrophe of the UV. Catastrophe of the UV. Okay. On the top of that, they could not measure the motion of the ether. Okay. And what was the ether? Let's put the ether here. Okay. At the time, and that's related to Einstein's theory. At the time, scientists believed that the vacuum of outer space was filled with an ethereal substance that was required for light to propagate, okay? And according to the, this substance had some the substance had some very unusual characteristics, okay? However, this theory of the ether started to fall apart when Albert Michelson failed to measure the relative motion of the ether. Okay, it was the most successful failed experiments in human history. Okay, today we call this failed experiment as the most successful failure in human history. Okay, think about that. You're doing an experiment, you're getting a result that you don't expect. And that's exactly what happens at that time. Okay, you're doing an experiment, you're getting a result that goes against everything that the scientific community believes, and you see that your experiments are incorrect, are wrong. That's what and when in reality, there was nothing wrong about this experimental result. Okay. That's what we call the most successful failure in human history. Okay, but the experiment was not a failure. Scientists thought the experiment was a failure. This experiment was successful. It was just the interpretation of the experiment that was incorrect. Okay, and that's what gave some of the support to Einstein's theory of relativity. And what was that they were thinking at that time, right? That came to this crisis that helped, unravel the crisis that physics was going through. Okay, at the time, scientists thought that there was an absolute referential system in which everything else had to be measured with respect to, okay? The so-called referential of the ether, okay? It should be the ether. It should be the ether that would be in absolute rest. That was the idea that they have been implanting in the minds of the scientists at the time. There was even PhD thesis that assumed the existence of this ether, okay, of this absolute rest referential, okay. The theory of the ether was necessary because scientists thought incorrectly, okay, that all types of waves required a medium of propagation. Okay, that's and the ether was necessary for this reason. Here you go. For this reason, the ether was necessary to justify the propagation of electromagnetic waves, okay? So they have this mindset, this incorrect mindset that light waves, electromagnetic waves, required a medium to propagate through space, okay? So this was an incorrect mindset, okay? Since we now know that electromagnetic waves can propagate in vacuum, since we now know in vacuum, okay? So for this reason, scientists were trying to measure the motion, not the motion, but the relative motion of this absolute referential with respect to the motion of Earth. Okay? And there was this guy that built a device that was capable of doing that, at least theoretically. Okay? And Michelson's device was Michelson's invention, right? Michelson's invention was a device that was thought to be able to make this type of measurement. Okay, today the Michelson interferometer, and that's where the most successful failure came about. You know, for Michelson's surprise, he was never able to measure the relative motion of the ether with respect to Earth. Okay, he got a negative result. That nobody could explain. Nobody at the time could explain. Nobody at the time could explain. Okay, until Einstein came about. Until Einstein came along. Einstein came along. First, Einstein he implied, right, that there was nothing like an absolute referential, an absolute frame of reference. In other words, the ether was a unnecessary supposition, right? Hypothesis. Then Einstein said something else. There is no every motion. What he said that every motion must be measured always with respect another referential. Okay, always with respect to another referential. Okay, And that's one of the Einstein's postulates, two postulates, okay? And that gave rise and that gave rise to Einstein's first postulate. Here you go. The relativity postulate. I'm going to take out the relativity postulate. Until Einstein implied that there was nothing like an absolute frame of reference. In other words, the ether was an unnecessary hypothesis. Every motion must be measured always with respect to another referential instead of this absolute ethereal referential. Okay, this gave rise to Einstein's first postulate, the postulate of relativity, or the relativity postulate. And what does it say? It says that the laws of physics are the same in every inertial reference frame. Okay? And the laws of physics means any of those laws that I mentioned before. Okay? The second postulate was a little bit more difficult to swallow because of its consequence. Not because of the way it was formulated, but because of its consequences, okay? A little bit more difficult to swallow. Not because of its formulation, but because of its consequences. Okay? And the way it's formulated is very simple. It's not difficult to memorize, but it's difficult to believe. It's difficult to believe, not because of the way it was formulated, but because of its consequences, okay? And I'm gonna spell that out too. Here you go for you all. And the speed of the light postulate. Okay? The speed of light in vacuum measured with respect to any inertial frame of reference will always be 300,000 kilometers per second, no matter how fast the source of light and the observer are moving relative to each other. So that's what you have to memorize. And memorize this one too here. This one is not difficult to believe, right? The problem is this one here. Not just to believe, but to understand. So let me give you some examples here. I'm going to explain to you what that exactly means. It's a postulate, okay? It's a basic truth we use this postulate to explain the universe. We do not prove it that it's correct mathematically. We cannot do that, okay? And I'm going to explain what this second postulate means. So here you go. Consider a referential at rest with respect to all of us, okay? And here you go. We have a laser source, a light source, laser or light source that is projecting a beam, right, in space. So far away from this laser source, we have a detector that's capable of measuring the speed of the light. Okay. In this case, both the referential and the detector, both referentials, right? The referential of the light source and the referential of the detector are at rest with each other. Okay. So let's elaborate here in my. First, consider a light source and a detector. The detector is far away. Is far, is far away from the light source. And don't forget, it can be a laser. Okay. And both the detector and the light source are at rest with respect to each other. Okay? The detector is capable of measuring the speed of the light, and it measures c as being 300,000 kilometers per second. So that's the first piece in our puzzle, right? One, right? First, consider a light source and a detector. The detector is far away from the light source, and they are both at rest. They are both at rest with respect to each other. The detector can measure the speed of the light, somehow, okay? And it measures c equal to 300,000 kilometers per second. Then we repeat the experiment in a different way. Let's get rid of that. Here you go. Referential A is for the laser, referential, A also for the detector, right? Detector measure speed equal to 300,000 kilometers. Now let's change the situation. Now we have the laser at the referential A and the detector at the referential B. And this referential B, the detector is attached to referential B. And this referential B is moving towards the laser beam, okay? So now, consider the laser, the light source, right? In the referential A at rest, and the detector in referential B moving towards referential A with a relative velocity given by relative velocity of A with respect to B, like that. Okay? Doesn't matter what's the value of this. Just assume that this detector is moving towards referential A with constant velocity. With a constant velocity, with a constant relative velocity, here you go, constant relative velocity of VAB. Okay? Okay, from, Newtonian mechanics, we would assume that the detector would measure a speed that would be according to Newtonian mechanics, right? The detector would measure a speed equal to 300,000 kilometers per second plus VAB, right? That's what would be bound to believe. But that's not what Einstein is saying. Okay. But that's not what Einstein, but that's not what Einstein is stating in his postulate, in his second postulate. Okay? Instead, he said that the detector still measures a speed of 300,000 kilometers per second. Okay? Okay, that's what Einstein postulate means. The same applies. The same applies. The same applies if the detector, if I shall be now, if the detector is now moving away from referential A with a constant velocity of A with respect to B. Of B, wait a minute, it's not A with, it's B with respect to A, right? B with respect to A. No. Let's see. No, it's A with respect to B, okay? It has to be. A with respect to B. Yeah, here you go. According to Newtonian mechanics, now we would say that the detector would measure a speed equal to 300,000 kilometers per second minus, right, the velocity of B, of A with respect to B. But again, that's not what Einstein is stating in his second postulate. Instead, he's stating that the detector still measures a speed of 300,000 kilometers per second. And I'm going to, show that to you again. Here you go. Now the detector is moving away. Yeah, it's B with respect to A. Okay, let's put that here. B with respect to A. B with respect to A. Again, this is not. Instead, he states that the detector still measures a speed of 300,000 kilometers per second. Did you get the idea? You must have this idea in your mind. Okay? No matter how the object, how the detector is moving with respect to the laser, it will always measure 300,000 kilometers per second. That's what Einstein is telling us in his second postulate. Okay? And it doesn't matter if the laser source that's moving towards the detector, okay? That's another, another situation. Okay? Now, here you go. I'm gonna repeat it, but I'm gonna repeat it in another way. Now consider the light source moving towards the detector. The detector with a constant velocity. And now we can say VA of B moving towards the detector with a constant velocity VA with respect to B. Okay? Again, according, and here you go. I gotta fix that on the other ones as well. Right in here, PB with respect to A. Yeah, here you go. Now consider the light source is moving towards the detector with a constant velocity. Again, according to Newtonian mechanics, the detector would measure speed, but that's not what Einstein is saying here either. He's saying that the detector still would measure 300,000 kilometers per second, and here you go. So 5 different situations, right? Moving away from the detector would still measure 5 different situations. And we get exactly the same result, okay? You get the idea? 1237. I want to emphasize that because it took me a long time to understand that. I felt that my teachers, my professor didn't explain that correctly to me. Okay, and now you can see this explanation right here in those illustrations, right? So let's review that. First, the detector at rest with respect to the light source, 300,000 kilometers per second. Then the detector moving towards the light source, but the detector still measures 300,000 kilometers per second, not 300,000 kilometers per second plus dBA, okay? Both devices at rest with respect to different inertial frames of reference. Then we have the second situation in which the detector is moving away from the laser source. It still measures 300,000 kilometers per second. And then we have this situation in which the detector is at rest with respect to us. It's the laser source that's moving towards it, towards and away. In both cases, the detector still measures a speed of 300,000 kilometers per second for the speed of the light. Okay? That's the 2 postulates that you have to keep in mind. Let it sink in you, okay? Start to believe this one is correct. You know, it seems kind of counterintuitive, exactly because, even for the scientists at the time, because they're thinking in terms of Newtonian mechanics. And what they discover later on is that Newtonian mechanics doesn't always apply. It applies only up to a certain point. And the certain point is given in terms of a speed. If a speed starts to exceed a certain value, then Newtonian mechanics start to break down. Okay? So you have to think in terms of Newtonian mechanics as an approximation to real life. Okay? That's what you have to do. So in summarizing, you know, Newtonian mechanics, although Newtonian mechanics is let's put it here, is a very successful, although Newtonian mechanics is a very successful theory, that allow us to predict many things, it still is an approximation to real life. Okay, an approximation to real life. I'm gonna tell you an approximation that breaks down whenever a speed reaches, whenever the relative speed between 2 different referentials breaks whenever the relative speed, here you go, between two different referentials becomes large enough. Okay, and large enough we're going to define very soon, okay? That's what you have to. We have a video series that is very good, by the way, explain, this concept that I'm teaching you here, okay? There is a video series, a very good video series in the internet. Internet, I mean the YouTube. That's called The Mechanical Universe. Has a very good explanation, and I highly recommend you to watch it on your own. The only problem is that there's a poor quality in the image. Okay, let me show you. Here we go. YouTube. Let me type it here. The Mechanical Universe. That's the animated series. Here you go. Let's see. See here. There are several episodes, but you want just on the theory of relativity. Mechanical Universe episodes on relativity. Velocity and time, the mechanical universe, relativity, the mechanical universe, okay? Episode 43, and there is another one too. Let's take a look at the Lorentz transformation, 42. Okay, the mechanical universe, Michelson experiment. Michelson-Morley experiment. The most success, okay, episode 41. So episodes 41, 42, 43, episodes 41, 42, 43, and maybe 44, okay? I want you to encourage you to watch that. And I want also Wikipedia, Mechanical Universe in Wikipedia. Mechanical Universe, there you go. You have a list of all those episodes, which was produced by Caltech. Okay, and list. Okay, list of episodes. We're talking about the last ones. Michelson-Morley experiment. Note that we just finished optics, right? The Lorentz transformation, that's 42. Velocity and time, and the energy, momentum, and mass. 41, 42, 43, and 44. Those are the episodes that pertain to this topic. Okay, 41 through 44. And the nice thing about those episodes that they explain a very easy to understand graphical sense. Okay. So I think we can stop here now. But before we finish, let's see here. Here are the sections, events and inertial frames of reference, the postulate of special relativity, and then next time we're going to start talking about the time dilation, okay? The relativity of time dilation. That's one of the effects of the consequences of Einstein's postulate. The amount of time that flows in one referential is measured differently from another observer that's moving with respect to each other, okay? That's what relativity of time is all about, relativity of time. What does it mean? According to this postulates, that's why people wouldn't believe that. According to these postulates, the time that you measure in one referential the time of that a given event, right? That two events happen in one referential, the time that that one measures, right? So that one measure. Let me see. Relativity of time. I'm gonna write that. Here you go. Consider two events. Okay, two events, one after another, separated by an interval delta t. Okay, consider a light that flashes and then a second light that flashes. Okay, the time interval between those two flashes. Consider two events separated by interval by a time interval delta t. Let's symbol. Here you go. If you are in a different referential that is moving with respect to the referential of these two events, okay, you will measure moving with a different velocity, right? Moving with a different velocity, relative velocity, with respect to the referential of these two events, you will measure a different time interval delta t prime. That's one of those consequences that difficult to believe that Einstein found out from his postulate. Okay, it's 12:49 right now. I think we can stop it and then we'll continue next time. Okay, so see you in 2 days, and then in the day after tomorrow we will have a lab, definitely. Okay, thank you for being here.
Have a good one, Professor.
Okay, see you.
Bye, Professor.
Bye bye.
Thank you.
Professor, I had a question.
Yes.
So, the next test will be on the 21st, and because right now I'm taking this class as a prereq for, or not a prereq, it would be a requirement, I guess, for my university because I go to Cal State LA, and my graduation is on the 21st,
Let's see.
and it's at 9 a.m.
What's the problem with the 21st? Let's see.
You have
21st
the
is the
exam?
exam. Is the exam.
Yeah, it's my graduation is 9 a.m.
9 a.m. Okay. Well, we can transfer to the other week, okay? But
Okay.
I have to do that for everybody, okay?
Okay.
So let's see how it's just the ceremony of the graduation. That's what it is. The graduation ceremony.
Yeah, the official ceremony.
The official ceremony. Okay, next time remind me of that, and then I will talk to the other students. Let's see if we can change to the other week. Okay.
Okay. Thank you.
Just keep in mind that if we transfer here to the other week, you're gonna have only 1 week between the third exam and the final exam.
Yeah.
Okay.
Okay.
Okay. What's
Thank
your name?
you.
What's your name?
Jacqueline.
Jacqueline. Okay. Thank you, Jacqueline.
Thank you.
See, I just taken time.
Professor, I have a question.
Yeah.
Sorry, so I know the lab 5 is due today.
Uh-huh.
I kind of have to go to work right now. Is there any way I could turn it in tomorrow?
Okay, let me extend a little bit more for everybody, okay? Let's see here. Cannot show that. Let's see. Let me stop sharing. Stop sharing and also stop.